Hi, good morning. Just recall what we have discussed in our last class. Last class we have discussed one lemma 6.3.5. Let a greater than or equal to 0 is an operator. Okay. Then there exists an operator x and it is unique such that x square equal to a and x greater than or equal to 0. Then there exists an operator x and it is unique such that x square equal to a and x greater than or equal to 0. We write root a for x. For x we can represent for root a we represent it by root x. Okay. Moreover, for all b such that ab equal to ba, it is true that root ab equal to b root a. Okay, for all b such that ab equal to ba, it is true that root a into b equal to b into root a. This is our lemma. Now, moving to our today's section, the lemma 6.3.4. If a greater than or equal to 0, b greater than or equal to 0, ab equal to ba, then ab greater than or equal to 0. A greater than or equal to 0, b greater than or equal to 0, ab equal to ba implies ab greater than or equal to 0. So, to prove this lemma, we are using this lemma. So, you have to know this lemma for proving this. Okay. So, for okay. Now moving to the proof. By lemma 6.3.5, for example, you must write this lemma. Okay. By lemma 6, there exists a positive root a for a greater than or equal to 0. Okay. Now to prove AB greater than or equal to 0, what we have to prove? We have to prove inner product of ABX x greater than or equal to 0. Inner product of ABX x greater than only. This is the definition of non-negativity. Okay, A greater than or equal to 0 implies inner product AX x greater than or equal to 0. So AB greater than or equal to 0 means inner product of ABX x greater than or equal to 0. Now what is we have to prove this. So to prove this we start with this one inner product ABX x. So A you can write as root A BX and all these are self-adjoint operators and we can write this as root A BX root AX. Okay. So again this you can write as AB equal to BA. We have this result AB equal to BA, B greater than or equal A greater than or equal to 0 implies root AB equal to B root A. Okay, so root AB equal to B root A x root x. So if you take root A x as some y, then what we get inner product BYY. Okay, but b is greater than or equal to 0. Therefore, inner product byy is greater than or equal to 0. Therefore, inner product abx x greater than or equal to 0, which implies ab greater than or equal to 0. Okay. So, once again, a greater than or equal to 0, b greater than or equal to 0, ab equal to ba implies ab greater than or equal to 0. For proving this, we are using this lemma. So, you must write this lemma in the proof of this lemma. Okay. Let a greater than or equal to 0, then there exists an x such that x square equal to a and x greater than or equal to 0. And in that case, root a b equal to b root a. Clear? Now moving to next proposition, this is also important. Let a be such that m into I less than or equal to a less than or equal to m into I. For some m comma small letter m comma capital M belongs to R and let P be a polynomial satisfying P of z equal to 0 for all z in the interval small letter m and capital M. Then P of a greater than or equal to 0. Once again, let A be such that m into I less than or equal to A less than or equal to m into capital I. Clear? Listen carefully. A be such that m into I less than or equal to A less than or equal to m into I. Okay. For some m comma m belongs to R. And P be a polynomial satisfying P of z greater than or equal to 0 for all z belongs to this one. Then we have to prove P of A greater than or equal to 0. So here we may assume m is strictly less than m. Why? This condition holds if m is equal to capital M equal to small letter m, this equality implies this inequality become equality, and this implies m equal to mi equal to a or equal to small letter mi. So if take p of z is equal to this one, some n polynomial degree n, then what is p of m? By this condition, p of z is greater than or equal to 0 for all z belongs to. Okay, so clearly from this, clearly p of m is also greater than or equal to 0. Okay. So what is P of m? P of m is a naught plus a1 m plus etc. a n m raised to n, and P of a is P of m I, and that's equal to this one, and which is equal to this. You can write as a naught plus a1 I m plus etc plus a n raised to m raised to n I, and this portion is greater than or equal to 0, therefore this is also greater than or equal to 0. This implies P of A greater than or equal to 0. Now next, so we are moving to okay. Since P of Z greater than or equal to 0, for all Z belongs to m comma m, we get that P of Z has real coefficients, and it may be written in the form P of z equal to C into product alpha I less than or equal to m z minus alpha I, product beta I greater than or equal to m beta I minus z into product of z minus gamma I whole square plus delta I whole square. Gamma I delta I belongs to R. Okay, for some c greater than 0. Why? P of z is a polynomial. Okay, P of z is a polynomial, and it may have roots. So suppose this is our small letter m and this is our capital letter M. So roots of polynomial may be here, may be here, and we can this is a polynomial, and we can factorize this polynomial. Okay, so this concept, what is alpha I? In need alpha I are in need alpha I are real roots to the left of m. Okay, so we are taking alpha I here, and beta I are the real roots to the right of m. Here P of z is a polynomial with as P of z greater than or equal to 0 means P of z must have real coefficient, and it is also non-negative coefficient. Okay, so we can write like this. Okay, and this as this is if we factorize this, roots are some alpha I means roots less than m, beta I means roots greater than m. So in this part we can write polynomial as z minus alpha I factorization, and in this part we write this as beta I minus z. Okay, and the quadratic factors take care all the real roots on mn. Okay, which must have even multiplicity and all of the complex roots. Okay, just so here if it has some roots here, then this you can write as some mm, z minus a. Okay, this term I will discuss you later how this term comes. Hope this is clear. Alpha I less than or equal to m and beta I greater than or equal to m. And this portion I will discuss later. Okay, and P of z you can write like this. Okay. Now, what about A minus alpha I? A minus alpha I. What about P of A? P of A, what is P of A? P of A is actually C into product alpha I less than or equal to M, A minus alpha I. Product beta I greater than or equal to M, A beta minus A. As it is operator, we can write I here. Similarly, beta I minus A and product Z means A minus gamma I plus delta I, gamma I square delta I square. Okay. So what is alpha I? We have alpha I less than or equal to m. Alpha I are roots less than or equal to m. Therefore, alpha I is less than or equal to mi. And mi is less than or equal to a. Therefore, alpha I less than or equal to a. This implies a minus alpha I greater than or equal to 0. So this term is greater than or equal to 0. Similarly, beta I greater than or equal to m implies beta I is greater than or equal to mi greater than or equal to a. This implies beta I minus a greater than or equal to 0. Similarly, we have this result also a minus gamma I whole square plus delta I square I is also greater than or equal to 0, which implies P of A greater than or equal to 0. That is what we have to prove. Okay. I will tell how this product also come later. Okay. Now moving to next corollary. This is a very easy last corollary. If mi less than or equal to a less than or equal to mi and p1t and p2t are real polynomials with p1t less than or equal to p2t for all t belongs to m in closed interval m, then p1a less than or equal to p2a. Okay. In an earlier case, it was mi less than or equal to a less than or equal to capital Mi. Then P is a polynomial such that P of z greater than or equal to 0. Then P of a greater than or equal. So here we are applying that result for the polynomial P2 minus P1. Okay. We have P2t less than or equal to P1t less than or equal to P2t. This implies P2t minus P1t greater than or equal to 0. So if you take this as our P of z, okay, clearly P of z is greater than or equal to 0 and correspondingly P of a greater than or equal to 0. That means P2 minus P1 of a greater than or equal to 0. P2 minus P1 of a means P2a minus P1a greater than or equal to 0. This implies P1a less than or equal to P2a. Okay. That's all for today's class. In the next class, we will discuss about projection operators. Okay.